So welcome everyone to this introduction to sender and receiver framework. Hopefully after the lunch you're able to grasp a pile of code right now and that you're ready for that, because fortunately or unfortunately you will see a lot of code in the presentation. Usually I don't like to have so much code on the presentation itself, but you will see it's pretty much self-explanatory. First of all, who am I? I'm a C++ software developer for around 15 years, and in the last 6-7 years I'm mostly working in the edtech industry. So basically whatever you have you wanted to talk about edtech, you can approach me and we can share some good ideas. Of course, the subject that I'm covering today is pretty much important in the edtech industry and async computations in general. Also, I'm a founder of C++ Serbia user group, and this is now a pretty large user group in Belgrade, Serbia, and every month there are more and more attendees over there on our meetups. So this is my email. If you have some questions after the talk, or please don't send anything during the talk, please send me. And first, like always, like in many presentations, a couple of disclaimers. So this is an introductory talk, right? So this talk assumes you know nothing about senders and receivers. It's marked as intermediate up to advanced or something like that in the schedule, but this is mostly because of the examples I've used. So you need to have some C++ background in order to better understand that. But all in all, this is just a basic story about senders and receivers. What is also important here, maybe someone would disagree, but we will only cover happy path. So we will not deal with cancellation today. Okay. So cancellation is completely out of scope. But first, let's go a little bit back and talk about multithreading in general. So when you hear multithreading, what are your first thoughts? So you don't have to answer me in general, but processes, threads, right? Atomics, mutexes, locks, a lot of locks, and even more locks. Okay, thread pools, executors, and some forms of lock-free programming in general, right? So in a sense, these are primitives that we are kind of used to. At least I think all of us here are kind of used to all of these in C++. But we are gradually moving forward. And when we are talking about multithreading, we have to make some notice with respect to concurrency and parallelism. So multithreading is not the same as concurrency and parallelism, and usually with among the people who are not so much involved in C++ or in general in programming, they put equal sign between multithreading and concurrency and parallelism, but these are not the same. And what can we say about concurrency and parallelism in general? What is the difference? So if you have a task and you want to execute a couple of them on different CPUs, you can have a couple of options, right? So if you have one core, the execution will be concurrent but not parallel, right? If you have multiple cores, of course, you can split things in a different manner, and you can have still some concurrent execution, but also you can have parallel execution as well, right? Because now you have two physical cores. usually when we are talking about concurrency, we are talking about our async model within our application and how we want to design our application to behave. So it's more like a behavioral thing. And parallelism is more about raw execution. How do you want to execute stuff on a bare metal? So there are a couple of scheduling guarantees, namely concurrent, serial, and parallel scheduling guarantee. And there are some differences in between them, but in general, concurrency requires somewhat stronger scheduling guarantee than serial execution. And I wouldn't delve too much into the examples, but maybe it's already clear. So when you have concurrent execution, you have to you need to take care of the things and how you order them in order to guarantee forward progress of your program, right? And that is why it requires stronger scheduling guarantee. On the other hand, parallelism is weaker than serial execution. And I mentioned that we are going back to basics, and let's go to, what is it, 13 years ago or something like that, to C++ 11. What did we get in C++ 11? We got something like this. Okay, so we got some primitives that we were finally able to use in our portable C++ code, right? So we wouldn't deal anymore with Windows threads, pthreads, Linux, and whatnot. And this was very good. This was a very good time for C++, and everyone adopted pretty well all of these things, all of these goodies that we have for 10 plus years already. But if you look at these things right now in 2024, personally, I see raw pointers, right? So all of these things are pretty much similar to what we think about raw pointers today, right? There is a mantra that nobody should use raw pointers in their code. I don't want to advocate that, of course, but most of the people can completely avoid raw pointers in their code base if they want. Maybe somewhere they cannot, but usually they can. And we are all using some form of smart pointers. I don't want to say standard smart pointers, but okay. So in that sense, these are more like raw primitives. And these primitives are something that we shouldn't think of when we design our concurrent applications. Unfortunately, in a lot of code bases today, we are still able to see proliferation of these primitives everywhere. So, and you can see a lot of these things mixed with business logic and whatnot in the code base. So it gets pretty ugly in a large code base. And at some point, somebody said, okay, we have to clean these things a little bit. What is happening today in 2024? So we have a couple of important proposals. So it's not 2024, it's a couple of years already, of course. But there is a networking TS proposal, which is not abandoned or something like that. It's still alive. And we have a unified executor proposal, which was the initial proposal for executors and for sender-receiver proposal. Then, of course, std execution is the newest proposal that is finally voted for C++ 26, right? And we expect that we will get something more than we got with coroutines. So we got coroutines in C++ 20, but we didn't get too much of a support for them. And personally, I hope that this will not happen with std execution. And of course, you have to make a peace between different worlds. So there is a proposal that makes peace between networking and senders and receivers. So some form of interfaces for networking. And whoever wants to refer how that looks like, you can refer to these proposals. I think that these are most important proposals so far, so we can go forward defining what are senders and receivers in general. So you can throw away all of these things that I've already spoke about, throw away all of these proposals, so let's go and see some examples. Okay, so I hope you can all see it. Okay, so we have some async computation, right? And we have a promise. All of you know, from at least if you used std future and std promise or boost variants earlier, how this works. You get some future from promise, and then you start some async computation, and when you are ready, when you have the result, then you set the value on the promise itself, and that's it. But there is one detail here that you don't want to do. You don't want to detach the thread like this. Please don't do that. This is just an example of starting async computation. Of course that you don't want to do that. But in the end, when promise sets this value, then future will get unblocked. I mean, you will be ready to consume the result. Okay. Then imagine you want to chain something on that particular computation. How would you do that? Well, if you use boost, you have .then on the future, right? We don't have it on std future. And you can do something like this. You can chain a continuation, right? And afterwards you can print the result. And the problem with this, well, a little problem with this is that you're attaching continuation later on, so after you already started your async computation, right? So in a sense, you have to somehow dynamically allocate the space for the continuation. And you all know, you all probably heard about how std future is fat or very heavy object and very heavy on dynamic allocation. And one of the reasons is also chaining the continuation and possibility to chain continuation once you already started async computation. And there is also a synchronization problem, right? So you have to synchronize somehow .then call and attaching this continuation once you already started your async computation. Okay, so if we don't need actually type erased continuation, can we do something different? We can. Hooray, templates. Okay, but imagine that you can pass a continuation that I've used before just as additional argument, right? So there you can imagine you can pass any callable, right? And as you can see here, the callable is directly used when you're about to set the value on the promise itself. So this is a place where transformation is happening. So it is the same as the previous example, but we are now calling continuation on the result of the async computation. Then we are setting the result of that continuation on the promise. And then the code looks something like this. And now this avoids some synchronization overhead and removes basically a race condition on reading and writing that continuation. Of course, don't get me wrong, the same thing can be achieved if, for example, you start or you generate your async computation suspended, right? and then attach continuation, and then after attaching continuation, you start whole work, right? So then it would be somewhat similar. Again, you still have type-erased continuation, and in this case, you don't have it anymore. And we are now in the realm of a lazy future. Let's create one. So we don't start async computation immediately. We just return a function that is able to receivers, that is able to receive a promise object and then to set a value on it, right? So in this case, thread is not yet started. We just returned a function, and we are able to chain continuation, again, like something like this. But in this case, we will pass this continuation as a promise, right? And we will use it. We will start a computation later once we call the actual function. And in this case, we have a lazy future, so it's not something that is started immediately. Then we can create our own then method, or I would say, or as Eric Niebler would say, then algorithm, right? So we can write our own then method in a way that, okay, I have a task, and I have a certain transformation. I want to return a function that is able to receive a promise, and also, when setting that promise, to apply this transformation that we already passed in. Okay. And a promise would look, that corresponds to the then algorithm, would look something like this. So set exception, of course, will just propagate exception, but set value will, as you remember already, first call transformation function on the result, and then that transformation will be set as a result to the promise. So again, we have pretty much the same code as we had before. So let's see how we can compose now lazy futures. So now you can chain multiple lazy futures like this, but then again, you have to stop chaining ticks at some point. You want to get the result at some point, and somehow you want to block, right? So in a regular case, when you use std future and std promise, and then you set the value on a promise, and then at some point maybe you didn't attach continuation, you just want to block. You can call .get, and it will block up until you get particular value. Here also we have to block somehow, right? And sync here is just a dummy promise that is able to receive the final value of this composed lazy future. But the problem is that printf is now in another thread, right? And main function here doesn't block, and we will have stdeterminate called. And now, as we had the then algorithm, there is you can also implement your own sync weight. These are all algorithms that already exist in Proposal. These are just some trivial examples how they can be implemented. And sync weight is used for these lazy futures to enable to basically block on them, to block on the particular tasks. And somehow now you're dealing with these primitives that we mentioned before, right? So these are now implementation details. So this particular algorithm doesn't know anything about async computation that we were executing, right? And this is the place where you are dealing with the particular implementation using all of these primitives that we had before. So you have to wait somehow when the data is ready, and when the data is set, you can inspect the state, and I will show how sync wait state looks like. And then when you get the result, you can just return it from the sync wait function in synchronous manner, right? And this is like a general approach how we can wait on things, right? You have some mutex, of course, conditional variable, and then you want to cover at least 2 cases if you are returning a particular value or you are returning an exception. You're setting an exception. And then sync wait promise here is again something that is communicating with the state itself. This is now the shared state, and this promise will set the data and wake up the thread, and we will get unblocked in our sync wait, and we can continue later on. And now this pretty much looks like this. We can now block, and this is a clean exit from the program. We will not have std-terminate called in this manner. So we used here 2 algorithms, and it would be nice to call them algorithms because you can compose them in different manners. Then and sync wait. And so far, we didn't use anything special, not from proposal itself. So these are just some basic concepts, but it's a different kind of, different way of thinking how you can combine tasks. Okay, so one more thing which is very interesting is that if you remember, async computation did thread creation at the first, right? And immediately created a thread. Then, in the second version, we had async computation that returns lambda, which itself creates a thread and starts the execution. But in both cases, std thread is somehow mentioned in async computation. And we can also abstract away the notion of thread creation into a new function, right? And if you think about it, we can really use this new thread like a completely separate function in which we will create a thread, and then async computation will basically chain all the things that it needs to do on that particular promise. And then you have something like this. So basically async computation doesn't know anything about threads so far. And this is very important example, very important notion that it's always good to separate your computations from raw executions and primitives and where exactly you want to execute your computation. You don't want to deal with it when you think of your concurrent application. At some point, you want to deal with it, but you want separation of concerns. So what are the advantages? So in this case, we can combine async tasks without allocation as we had with std future. Of course, we can avoid synchronization problem and some of the type erasure problems that we had with STD Future as well. One other advantage is we can now think of in terms of generic algorithms that we have. So then is a generic algorithm, sync weight is a generic algorithm, and in a proposal and in various libraries, there are a bunch of generic algorithms that you can use independently of what you are trying to do or where you're executing your computations. Think of it like STL for async computations, something like that. And with that, I propose that this could be a new C++ mascot. Tardigrades, pretty nice animals. I saw it, I mean, Neil deGrasse Tyson had one documentary and he was talking about tardigrades. They are pretty special creatures on our Earth because they can survive everything. Tremendous amount of heat, tremendous amount of cold, and they even survived in the outer space. So they are much like C++ programmers, I would say. We can survive everything, right? So independently of what they throw to us, I'm a mere mortal, and I'm looking into all the standard proposals, and I'm usually feeling like somebody is throwing something at me at some point, and I have to survive somehow from one standard to the next one. So yeah, they are very tiny creatures, but size doesn't matter. Okay, then we can continue with real meat and real proposal here. So this is the STD execution, and these are senders and receivers. And this is the sentence from the proposal itself, that this is a self-contained design for a standard C++ framework for managing asynchronous execution on generic execution resources. Okay? I'll give you 1 minute to contemplate on this sentence. No, let's continue. Okay, again, some motivation behind it. We want some idiomatic way to express our async computations. I will talk about it a little bit later, but it's not only about async computations, but mostly it's about it. Then, as C++ developers, as tardigrades, these little animals, we are dealing with a lot of obstacles, and there are different libraries in our world, right? The most prominent one, I would say, ASIO, right? So Boost ASIO or standalone ASIO, whatever you use. This is something that is 20 years or something like that here already, and it's pretty stable, I would say. Sometimes they break some performance, but overall it's pretty much stable, and it has a stable API. And what is most important for me, for example, when we talk about Boost ASIO, is everybody got used to Boost ASIO. So whenever you start to write your own HTTP server, right, you're kind of always you converge to something like Boost ASIO, right? So we are kind of stuck in that mental model. I don't say that this is bad, but I think that most C++ developers are usually going into that direction. And it is important that we combine these APIs all together somehow. And sender-receiver proposal is about that. How to combine different worlds, different APIs into some abstractions that are the same, that would be the same across every project. So there are three main concepts important here. schedulers. And what is a scheduler? Lightweight handle that represents some strategy how to schedule your computation on execution resource. And I'm talking about execution resources. So what is an execution resource? It can be a CPU, it can be a GPU, it can be, I don't know, whatever, or you can do it like in a way that execution resource can be whatever, because NVIDIA is mostly behind senders and receivers. I think that GPU will be the most prominent second popular execution resource after CPUs. Then we have senders. Sender is something that represents a unit of work. So we will see how some different senders look like. But basically, this is the unit of work, unit of computation, or even some data that you lifted up and you want to pass through your async graph. And on the other hand, there are receivers. Receivers are just callbacks. So we all used to use callbacks, right? But callbacks with 3 different methods this time. So we have a so-called value channel. We can set the value. We can set exception, right? And we can stop the execution. And as I mentioned, we will mostly talk about set value channel here in this presentation. And this is, now let's go to some, they call it a hello world example of senders and receivers, right? So you have a thread pool. This is your execution resource here. Now you want to abstract the way that you are using a thread pool as execution resource, and first thing what you're doing, you get the scheduler from the thread pool, and from then on you communicate only through the scheduler. And then you want to schedule some task on that particular thread pool. If you remember the function new thread, which created std thread object in the previous example. What we have here with scheduling on this particular scheduler is basically the same. So we schedule, we don't do any computation so far. We don't print anything, we don't calculate anything, but we just want to schedule something on a thread pool. This is the first schedule call. And then we are saying, okay, now we want to execute something on that particular scheduler. What are we doing? We use then algorithm, and we chain our async computation as a continuation on that particular scheduler. Okay? And then we can chain another one. And here is your int. Another example, this is also, well, second hello world example. Again, some thread pool, and if you want to execute some of the tasks in parallel, right, then you can say, okay, please schedule everything, first get the scheduler, right, and then schedule everything on three tasks on that scheduler, let them execute in parallel fashion, and then wait for them all to complete with the execution, and you basically want to print out the result once all the tasks are completed. And this is what we are doing here. I think that for the most of you, this is familiar already, at least when all or some kind of things, this is already in Boost. And then again, we are waiting with the sync wait here, and we have our values ready to print out. There is a slightly more complicated example, because now the question would be, okay, you showed us how to build execution graph basically in a compile time, but what about a runtime? I want to decide to diverge somewhere in runtime based on some runtime value. And this is how we can do it. So basically, we are now creating a new sender, and based on this value, we can create either one just sender, either the second one, so even or odd. And let value is an algorithm that allows you to do that. So let value is an algorithm that is able to accept this function, and in turn it forces you to return a sender. So let value forces you to return a sender that you will chain upon something else. But dynamically you can choose which sender you will return. And this is, well, I would say minimal control flow API, and minimal set of functions which are important in the senders and receivers. So you want to be able to start your execution even if you have only one particular value. You have to imagine you have an int, and somehow you want to lift it up into sender-receiver world. Then you need just algorithm. Just will do that. You need to chain continuations. This is a then algorithm. You need somehow dynamically turn the paths around. So you want to go left or you want to go right into your graph, right? You will use let value. I skipped on algorithm, which is of course also very important, and that is you want to choose where do you want to execute your graph. And at some point you can switch. If you executed your work on one thread pool, on a scheduler that you got from one thread pool, maybe you will decide that, okay, rest of the work in this graph I would like to execute on a different thread pool, on a different execution resource. So maybe some operation that is a better fit for GPU, you want to schedule it on a GPU execution resource. The point is that you will get combined graph of your async computation, which is pretty much agnostic of the execution resource below it. So with these simple algorithms, you can diverge it wherever you want. So I will be a little bit faster here. Some other familiar concepts that are related to senders and receivers, that is continuation passing style, monads. I don't want, there are a lot of, there were a lot of talks about monads. We can skip that. But basically, senders are monads. And these are some examples just to complete the picture. What is a continuation passing style? But I suppose you all know that. You don't return a value immediately. You are able to receive a continuation, and then you just call that continuation with the result that you do. So sender receivers are basically based on that. And as I mentioned, sender is a monad, and monad through 3 different channels, 3 monads. So value, error, and stop channel. And whoever is doing Haskell here, raise your hand. Okay, one person. That's fine. So there is some mapping between some of the algorithms in the sender-receiver proposal and Haskell. So just is something that lifts concrete value into a sender. That would be a pure. Then we have then algorithm that would act like fmap, right? And then we have a let value that would somewhat act like bind. Okay, so now what is maybe a bit more important for all of us, as I mentioned, mere mortals, that we want to use new stdexec library. How do we combine, let's say, all of these new goodies from the library with our own code that we already have? And what's needed, what can we do to satisfy the concepts from sender-receiver library? I think that I didn't mention the presentation itself, but it's worth mentioning that I think one of the first implementations was libunifex from Facebook, and there was a statement almost 2 years ago that is heavily used in production, and I think Facebook and Instagram already use libunifex. So it's not something that is just in a pure theory. There is already some usage in the field. And libunifex pretty much diverged from P2300 and stdexec from NVIDIA is stick to it so far. So we mentioned a couple of algorithms. We mentioned that we want to lift simple values into sender-receiver world, right? Let's see how we can do that with just two simple algorithms, I would say. Just, I still call it an algorithm because we lift the value, and then algorithm. And now one simple note is that for connecting all of these things, I'm using connect from stdexec library. But I'm not using algorithms from stdexec. I'm not using stdexec then, and I'm not using stdexec just. So we can implement them on our own. Second example is pretty much the same, but it was about to show how you can use sync weight algorithm from stdexec and not to implement your own. So implementing your own sync weight is probably not so difficult, but it's somewhat error prone. So if you can use it from the library, it would be much better. Okay. So this is how just sender would look like. So we have to satisfy some of the concepts from stdexec, and this is all mentioned below stdexec comment here in the code. So we have to somewhat mark just sender that it is a sender. This is a sender concept type here. Then we have to define completion signatures. What do we want to support in this case? In this case, this is just a pure case of lifting a value into a sender. So we just want to have set value here. This, I would say maybe ugly macro here. I left it out intentionally because it's used across stdexec examples. But it's just a macro that turns this connect method into a tag invoke. So basically this will be a tag invoke function which accepts connect tag, right? Everything else is the same. And this For the first argument, for self argument, this is not deducing this. This is also used, this is followed by the macro in order to be able to mark self as something that we will call upon for setting the value. So connect is a method that takes a receiver, takes sender as a first argument, then a receiver as a second argument, and creates an operation. Operation is not started yet. We have to call start on the operation, and then the execution of the whole process, will start. So basically, this is the schema across all the proposal. You have senders, you have receivers, you connect them, you have an operation, and then you are ready to start the operation. One important note is if you do not implement your own senders and receivers, I think that you would not need to do that as much once we get std execution and maybe some supporting libraries. Then you will not see receiver concept. You will mainly deal with, on the API level, you will mainly deal with senders and operations, I think. You will not see receivers so much. Here we have operation, and as I mentioned, we have to start operation somehow. What is a start for a just algorithm? Well, you just set value that you got. Okay, so basically you set the value from you set the value that you got from the sender. And where do you call the set? You will call the set, this is also important, you will call the set on the receiver. So this is just a customization point, and basically you can read that line as you would call set value on the receiver itself with a value. So your fancy callback is being called with a value. Again, this is how, let's say, then sender would look like. There is something that you have to satisfy. Also, you have to mention completion signatures. Here, you want to set arbitrary value. That's why you have to first deduce what was the value of initial sender that you're attaching upon. That is why this result underscore t is used in the completion signatures. You also want to set exception. You want to be able to set exception, and of course you want to cancel. You want to cancel the operation if it's possible. And then you have to implement again on this sender. You have to implement connect customization point. Why is this important? You have to connect up. Now you have to connect a particular receiver. So this is a little bit different than a pure just case. Now you also have this receiver that you want to connect with. Then operation is pretty much simple here. You just want to start inner operation. And then receiver, it pretty much resembles what we already talked about with then receiver at the beginning of the presentation. You need to have set value, set error, set stopped, and then what you will do, you will call basically all of these methods on the underlying receiver itself. But again, as you can see, first we will do the transformation. So I'm not calling receiver in a set value customization point directly with the value, but first I'm calling a function that was embedded in the then receiver. Then I'm getting the result, and with that result, I'll call set value on the underlying receiver. So it's like like an onion. You're piling things up, and you're piling onion, and then this is how execution looks like. And for the sake of completeness, for the full example that I have later on, this is how the most simplest receiver would look like. So you just announce that this is a receiver, that this satisfies receiver concept. You specify all customization points here, and you can do whatever you want. Full working example, maybe you would like to take a picture. Full working example is here. So it's always better to execute that on your own. Godbolt is very good because you can use std execution. You can define it as a library, so you can choose it as a library already. So whenever you want to play something with std execution, you can do it on Godbolt as well. So this is a full working example that you can debug of what we. Last but not least, I didn't mention, maybe I mentioned only once, coroutines. And there is a connection between coroutines and senders and receivers. So these are not the opposite things. So for all of you who are already into the coroutine world, this is senders and receivers are not an opposing proposal. So this is a completely different thing. And of course, you can combine them with coroutines. And in theory, except maybe error channel and cancellation, they are pretty much mapping one-to-one. So all awaitables in coroutine world are senders. So this is something that you started. This is some async computation, or you can choose to wait on it. Basically, waiting on it, you're attaching continuation, because whenever you do a co-await on your awaitable, everything below it can be executed somewhere completely on some different execution context. Many senders, when you have senders that return multiple values, this is an interesting case. They can be relatively easy made awaitable. And as I mentioned, senders, receivers in general, we are expecting them in C++26, and I really hope that we will have more supporting libraries. So there are already, I think that there is also std execution implementation in the Beeman project. I think that this is the newest implementation, new kid on the block. But there are various libraries, and I really expect that we will get a lot of library support, because in the end, if we don't get library support, I think that this will end up as coroutines in the real world. So everybody has his own implementation of tasks and something like that, and we do not have still coherent things in the coroutine world. With that, I would say thank you.
Any questions?
Thank you. Thank you for your talk, first of all. And I think I just have one question. It's probably more coming from like the semantical view, not necessarily what you have presented so far. And my question is that in many cases, what I've seen so far, these asynchronous libraries compromises a lot on readability and code locality and maintainability. And basically what we are talking about, if you think about it, a function is nothing else, just a monad of expressions, right? So if I write a blocking function, I actually get what you presented here. The only difference is that I will use the thread as a resource. And when I'm blocking the thread, that's basically using a stronger resource than this light resource what you presented. And my question is that, you know, in modern operating systems, you can spawn a couple of hundred sets, and it's not really an issue. So I would say there is a sweet spot when I would want to use your library, because in the basic cases, I will just write a blocking function and just spawn a thread, and I don't care about it too much because of this readability issue. What I said, for me, the readability works in many cases more than this kind of heavy-handedness on the resources. So what would be your what would be the sweet spot when you would say, like, okay, if you want to have like 200,000 concurrent tasks running, that would be the sweet spot when you start using this, or would it be 100, or what's your opinion on this in general?
Immediately, I don't know why, because sweet spot between readability and execution speed, I think that sometimes this is a matter of preference, but usually it doesn't mean that you have, if you have a more readable code, that it is a priori less performant. So all of these algorithms can be combined in a way that you can get, I don't say that you will, but you can get maybe the same performance as you would write it on your own. So there are a lot of use cases. For example, you want to have some affinities defined. You want to execute some of the works to a specific execution resource and keep them only on that. You want some stickiness to execute only on that execution resource. Some other tasks you want to execute only on some other execution resources and whatnot. I don't know if this is already covered, if you can do such customizations. Also, maybe there are some problems with in general with reusing some of the fast collections. Maybe you have some fast collections in your system then that you can reuse, and that would be quite difficult to convert into, let's say, to send a receiver model and to use it with these algorithms. But the thing is that the idea of this proposal is not to enforce you to write a completely different code if you don't want to, but that you are able to adapt also your code and to plug it in into something else. So to combine it with something else.
Okay, yeah. So I think so. Where my question was going is that in practice, if we can write like that, because the chain of events what you described in your presentation, that's a function, right? Where we have an asynchronous blocking operation in the middle.
Yeah.
And what motivates you to use this technique instead of just creating a thread, let the thread be blocked, and let the operating system scheduler do exactly the work what you are doing here manually?
The main motivation, at least for me, is a separation of concerns. So I would really like to be able to still use C++, but for when you're working in a larger group of people, right? And you have some novices, you have maybe less experienced people. There are a lot of mistakes that can happen if everybody is using the primitives. Then it turns out that you have to define some guidelines. So your company or your team ends up using some code guidelines for using all of these primitives. So from my point of view, this is an overhead, at least a mental overhead. And although this is something we didn't used to, I think on the long run, it can reduce mental overhead, because you're really not thinking anymore in terms of threads, futures, and something like that. Of course, if you need to implement something like that, you can go back to the trench, implement your own senders and receivers, right? But it is completely decoupled on how it is used. For me personally, this is a good approach. This decoupling. I mean, main motivation.
Just a quick response to this last statement. So we built a similar design in our company, works a bit different, but our goal was also to abstract from these low-level multi-threading primitives, and it really helped us a lot. So I think it's a good direction to go. Continuing on these type of frameworks. So.
One thing I didn't ask the audience, I wanted to, is how many of you in this room are actively using C++ ranges? C++ ranges. C++ 20 ranges.
In production or in general?
In production, please. There are some hands lowering down when I said production. You see, that is what I mean, somewhat. Okay, so I would now expect that I see all of the hands raised, but it's not the case. And you should ask, we should ask ourselves, why is that the case? So first, we have a lot of things in our code base that it's not so easy or it's costly to convert and to use C++ ranges. And there is another problem common to the problem that we are now talking about is mindset. So switching yourself from kind of a procedural way of thinking into the realm of almost functional programming, right? This is the same thing is happening here. So we all got used to write in a procedural manner to create our own threads, to even to join them on our own, right? Why would we use RII when we can join them manually, right? And our own callbacks and whatnot. So this is the similar problem, I would say. So switching the mindset from what we got used to do in the past 20 years to something that looks like a novel thing, but again, from my humble point of view, is something that we should strive for. And this is complete decoupling of what we are doing. And I think that in 2017, Kevin Henney was, or 2018, I cannot remember, Kevin Henney was here at Meeting C++, and he had an awesome presentation about declarative programming. This is a declarative approach. So you would like to define your graph of execution in a declarative manner because it will be contained in almost one place, and you can have some local reasoning about what is happening in your code base. Creating threads, tasks, spawning them, I don't know where and how. Okay, you can spawn them every time on a particular thread pool or something like that, but this is pretty much hidden, right? And buried underneath. And this is why declarative approach is more appealing. Ranges, again, are more declarative approach. This is more declarative approach. And a couple of these things in C++ strive to the same direction, I would say.
Unfortunately, that's all we're going to have time for right now, but please feel free
you can find me around, you can write me an email. I will be on our communication channels on Meeting C++, so yeah. Thank you.